Image edge detection, ED, is a fundamental task in computer vision, aiming to find edges in an image. Despite significant progress in ED algorithms, current models still suffer from unsatisfactory precision rates, especially when a low error toleration distance is allowed. Moreover, models often produce unsatisfactory edges on noiseless data, namely edge maps themselves. To address these issues, this paper proposes novel ED models with cascaded skipping density blocks, CSDB, and a novel modification on data augmentation for training. The proposed models, named Skipping Density Precise Edge Detection, SDPED, employ very deep structures with CSDB, which have not been considered in ED tasks yet. Unlike previous models, SDPED does not require supervision in different scales, demonstrating the unnecessary of multiply-scale supervising. The models obtain state-of-the-art, SOTA, predictions in several datasets, especially in average precision rate, AP. The paper also proposes a novel modification in data augmentation, allowing ED models to employ noiseless data for training. This approach enables models to produce more satisfactory results on noiseless data. The effectiveness of the proposed data augmentation method is demonstrated in Figure 1, which shows that the model retrained following the proposed data augmentation provides more precise predictions on edge maps themselves. The paper reviews previous works on ED tasks, including datasets, preprocessing, CNN-based ED models, and loss functions. The datasets reviewed include BSDS 300, BSDS 500, NYUD, NYUD2, Pascal VOC, Microsoft Coco, Scene Parse 150, Cityscape, MDBD, Biped, Brind, and UDED. The paper highlights the limitations of these datasets, including the unavoidable noise in human annotations. The paper also discusses the importance of data augmentations in ED tasks, which usually include image rotations, flips, crops, resizing, and gamma transformations. However, the augmentation procedures differ from paper to paper, and the validity of mass augmentation has not been thoroughly investigated. The paper discusses the development of a new edge detection model, SDPED, which utilizes cascading skipping dense blocks, CSDB, in its main path to provide multiple outputs that are then fused by a fusing block. This model is designed to address the issue of obtaining crisp edges without post-processing, as most CNN-based models cannot achieve this due to max-pool operations and the use of weight binary cross-entropy, WBCE, as the loss function. The authors also explore various evaluation methods for edge detection models, including calculating optimal dataset scale, odds, optimal image scale, OIS, and average precision rate, AP, based on the F-beta score. They note that the error toleration distance, a hyperparameter in the evaluation algorithm, has been inconsistently employed across different datasets, leading to varying standards. In terms of methodology, the SDPED model employs CSDB in its main path, providing multiple outputs that are fused by a fusing block. The model uses weight binary cross-entropy loss, LWBCE, as the loss function during training. The authors also propose improving the performance on noiseless data by adding labels to the training set, which can be considered as noiseless data since they are the ground truths being employed. Furthermore, the paper discusses the importance of selecting a suitable error toleration distance for evaluating models on a given dataset. The most commonly used algorithm for this purpose is the one provided in 7, which calculates odds, OIS, and AP based on the F-beta score. However, the error toleration distance has been set differently across various datasets, resulting in inconsistent evaluation standards. The paper discusses the evaluation of edge detection, ED, models, highlighting the inconsistencies in error toleration distances used in various datasets and proposing a standardized approach. The authors argue that the error toleration distance should be set to an exact length of pixels instead of a ratio of the diagonal distance, ensuring evaluation independence from image resolution. They also suggest a strict error toleration distance of 1 pixel, considering human annotations in current datasets have a 1 pixel deviation. The paper then describes the experimental settings and benchmarks used to evaluate the proposed model, SDPED, on 4 datasets: Brind, UDED, MDBD, and Biped. The model is trained with data augmentation, and the optimizer is set to atom with a weight decay of 10^8. The learning rate begins at 10^4, and is divided by 10 after every 50 epochs. The batch size is set to 8, and lambda is set to 1.1 in equation 1. The evaluation results show that the SDPED model obtains state-of-the-art SOTA results compared to previous models, with improvements of 2.7% on odds, 3.1% on OIS, and 6.9% on AP on average on the blind dataset. Similar improvements are observed on the other datasets. Ablation studies on blind and UDED verify the effectiveness of the skipping dense structure and the multiple-layer fusing block. The authors attribute the improvement of the SDPED models to 3 reasons. 1. The absence of downsample operations, which prevents information loss and increases uncertainty. 2. The ability of the backbone to deal with textures, which is beneficial in ED tasks. And 3. The design of the CSDB, which helps distinguish edges from textures by finding areas with the most response. The research paper discusses the SDPED7 model, which demonstrates significant improvements in edge detection tasks across various benchmarks. On blind, the model achieves the best results in all 3 experiments and benchmarks, with an average improvement of 2.7% on odds, 3.1% on OIS, and 6.9% on AP. The SDPED model also outperforms others on UDED and MDBD, showcasing its versatility and effectiveness. The results indicate that the model's architecture could be more efficient, utilizing fewer coefficients compared to previous models. This efficiency and performance make the SDPED7 model a promising solution for edge detection tasks. The paper presents a novel precise edge detection model, SDPED, and a modification on data augmentation to improve the performance of models on noiseless data. The model obtains state-of-the-art results, especially in improving the AP, over multiple datasets and different partitions, demonstrating its precision and flexibility compared to previous models. Furthermore, the number of coefficients employed in the model is less than half of the previous state-of-the-art models, illustrating its structure could be more effective and efficient. The modification of data augmentation provides the first method to employ noiseless data in training edge detection models, which could be widely employed in the future. The ablation result on blind and UDED datasets shows the validity of the structures. The results demonstrate that the skipping connections and the final fusing block are essential for the performance of the model. The model's size is significantly smaller than previous models, such as HED, RCF, RIND, BDCN, and DEXI, while maintaining or improving their performance. The paper also discusses the challenges in defining edges and textures, as well as the limitations of current datasets for edge detection tasks, which are highly dependent on human labels and thus contain unavoidable noise. It suggests further investigation into how to obtain noiseless data. In conclusion, the paper presents a novel edge detection model that achieves state-of-the-art results with a more efficient structure and provides a new method for data augmentation. It also highlights the challenges and limitations in edge detection tasks and suggests future research directions. The paper discusses the advancements in edge detection techniques, particularly focusing on deep neural network (DNN)-based methods. It reviews state-of-the-art datasets and techniques, highlighting the progress made in this field. The authors also explore the question of whether edge detection has been fully solved, considering the current capabilities of DNN models. The paper cites several key studies that have contributed to the development of edge detection algorithms. For instance, Deng et al. 2018 proposed a method for learning to predict crisp boundaries, which was presented at the European Conference on Computer Vision, ECCV. This work demonstrated the potential of DNNs in accurately identifying edges within images. Furthermore, Wang et al. 2019 introduced the Enhanced Super-Resolution Generative Adversarial Networks, ESRGAN, which significantly improved image quality by enhancing edge details. This approach leveraged the power of generative adversarial networks, GANs, to refine edges and produce high-resolution images. Mubashar et al. 2022 conducted a comprehensive review of edge detection techniques, assessing the performance of various DNN models on different datasets. Their findings suggest that while significant progress has been made, there is still room for improvement, particularly in terms of robustness and efficiency. In conclusion, the paper provides an overview of recent advancements in edge detection using DNNs, highlighting both the achievements and challenges in this area. It emphasizes the ongoing need for research to further refine these techniques and address remaining limitations.